This is a video about my interlocking fire protection panel system that I initially developed for use in fire training facilities. But this system has many diverse applications for use beyond just fire training centers, and you can make the panels into any shape, size, and or texture for, again, the different applications that you might have in mind.
Okay, today I want to go over a panel system that I made, an interlocking panel system that was specifically designed to install as a protectant, a liner, in fire training centers where firemen are trained. They build fires inside of the buildings and the guys go in and try and put them out. All of these buildings are made typically with poured concrete walls and floors and roofs and ceilings and such, or block, CMU block that's laid up, and or a metal building like a warehouse is made. None of these buildings can take the constant evolution of fire being burned inside of them. The building will succumb and will no longer be certified for occupancy of training firemen in a safe manner. So the industry is using, or was using, a product called Marinite, which is like a drywall. It's not drywall, but it's a lightweight, and they line the system and it lasts up to 1 to 3 years, and then they got to replace it. Well, a gentleman approached me he built these fire training centers, approached me and said, can your mud take 1,200 degrees? And I said, it's cement, and I would think it would, but I wasn't really sure. So we started making some formulations and testing them, and we ended up with this system here, which is an interlocking liner system. It's 1.5 inches thick, and it's got a ship-lapped edge, and on the face, where the fire is burning, this can take 2,200 degrees, and we had thermometer or thermal reading devices, probes, that were behind in various locations, the roof, the ceiling, the floor, all that. So we were trying to get the data. On the back side of this panel was only 150 degrees. Now in the past, the gentleman that approached me had used other cementitious materials, and they spalled, they blew up, they exploded. And the reason being is regular concrete and mortars are porous, and the water can invade. When the firemen are putting out the fire with hoses, they're wetting the panel, and the cement gets inundated with water because of the porosity, and then the next time a burn happens, that moisture that's in, or that water that's in the panel is getting hot, and it turns into steam, and it wants to evacuate the material, and it doesn't quickly, and next thing you know, it expands and it blows up. And the image that I'm showing you now is one where outside of my rock wall, which is made out of a mortar, in the river area, I built a little fire to burn some slag lumber that I had, and I had the fire going there. Within an hour of that fire being started, I heard this big pop, boom. It was like an explosion, and pieces like shrapnel came by me of the rock. It had gotten so hot, it blew up. It rained the day before, and it was moist, and the fire got hot, and boom, it popped. So this particular formulation is one that takes high temperature and is not porous and is strong, so it does not succumb to the normal elements of heat. The big thing is thermal shock. A panel's cold and it gets heated up, and then the firemen douse it with water. That thermal shock can shatter a cementitious product. This has been since 2009, and it's 2019 now. This has been used all over the world by this company building these fire training centers with my liners. At any rate, I have wanted to show you this, and now I'm making a video of it, so I'm going to go over some of the prospects of how to use it and what it's all about and that kind of thing. I started the process of prototyping these panels out of just plywood. I actually cut these and made them and mounted them to boards, and I think I made a total, I've got 6 here, I think I made a total of 9 of these, and they interlock, and we checked them out for their compatibility and installation and all that sort of stuff. And I said, okay, this is the system, this is what we're going to mold. So we mounted these to boards, and then we made molds every day. For 9 days we made 9 molds. We had 9 prototypes, so we could make 9 molds a day, and that's how I figured out what I wanted to make in prototypes. I needed 9 days to make them, and we made a bunch of molds, and I'm now showing you an image of the molds in our shop on the pallet racks. And we would cast these every day, and we built and made products. So at any rate, making a prototype today, I would CNC it. There was even though I tried, I mean, I cut these on my table saw and I routed them and did things all with hand tools. And in measuring these, I mean, with a micrometer, there is up to 3/16 of an inch difference in the lengths of some of these panels, which as you're going down a row of these, that compiles, that builds up, and it's not good. A lot of times, like putting on the washers that actually secure this to the wall, if you have a growth, it can be a problem in these lining up to where this washer that secures 4 corners at a time will actually fit. So today, if I was to make these, I would actually do it out of aluminum, and I would do it with a CNC process to where, let's just say I was making 9 prototypes again, every one of them would be exacting. Where these are, in a slight fashion, they're off, and that's not cool. So again, making a prototype, whatever you make and you mold, that profile, that image, everything about it goes forward in every casting that you do. And there can be a problem if you don't have exacting, how would you say, conditioning of your prototypes. Now, a lot of the rock and stone that we've made molds of, it's not so critical, but in this system, it is very critical. So there now with the new system that I have that I'm going to show you, there's 10 thousandths tolerance. That's nothing. A hair is like 6,000. And so it's very exacting. Again, CNC processes are the way to prototype in this particular case. Now, I wanted to go back over the actual way. Once these, as you're laying these panels to secure them, you're basically taking a screw into, well, first let me back up. The building is always lined on a 16-inch center with these hat channels. And you screw these to the building. The idea here is we want an airspace between this liner system and the building. 2 reasons. One is just it helps to dissipate heat through airflow. There's ventilation put in both the top and the bottom so that there's a circulative airflow and you can cool down. So there's no heat ever going to be on the building. Second thing is water. As the firemen are blowing that water, this system has 2 things. One is it's shiplapped and it's like a roofing tile. I've got it backwards. This tile will drain the water down and it doesn't let the water go behind. So, and if water did get behind, the system is not cemented or caulked together. It can actually drain out of the panel system. And in addition, as the heat expands and contracts through temperature change, this panel can move and still have a fire impingement protection. Fire impingement is just a fancy way of saying the fire can't get through the joint here between these shiplap pieces and get to the building. Fire impingement is not something you want happening. So again, this system was well thought out in all regards to that. But this is just usually, this is just a piece of steel. Usually they're stainless steel. Again, the water with this thing would rust if it was just regular metal. So stainless steel screw washers and screws are then screwing into the hat channel, and that's why these are self-tapping screws, because they're going to go into this. This was, instead of each panel having multiple screws, by using this washer design, we could use 1 screw to secure 4 corners. We diminished the screw count by over 50%, more than that, I think. At any rate, I don't recall, because this design was done to where the washer would inlet into those and keep them aligned. Now, forgive the illustration here. These panels are horizontally oriented. Usually, they're vertical. Now, we also line the ceiling inside of the room, and then that was a horizontal application. But this table is very unlevel, and for me to even set this in here, it's got 2 tables that I put together, and it's not real straight. But anyway, the idea is that I just kind of wanted to show you the layout. Again, this particular panel has the Maltese cross, the Fireman's Maltese cross, molded into, the mold. We actually had lasered in the wood the actual image where we had it done, and when we molded that, we picked it up. So every casting would also have that Maltese cross. Now, I also made some panels that didn't have the Maltese cross, and that was because a lot of times when you're fitting a room, you're going to have a small piece over here. We didn't want a half of or a quarter of the emblem showing. So we in the corners, on the floor, in the ceiling, wherever there was a smaller piece of panel, we used the non-Maltese cross panel so that it would look good. Since I've made this system, I came up with, I think it was back in 2015, where I said, this washer and the way that this fastens, and the way we had to mold it was a little, or cast the panels was a little burdensome. So I came up with a new system which is a little different. Now keep in mind, this is a 16 by 16 inch face, which is 1.77 square foot per panel. We came up with this because you got a guy that's literally hanging these panels up, and you want this to where he can pick it up, and it's not two guys that are, you know, we could have made a 4 by 8 panel. Why didn't we? We could have made a 8 by 8 inch, like a tile, you know, a small piece. We made this because it was the perfect size. So I came up with a different panel, which this is a prototype, a quarter scale prototype. So basically the panel now is 8 inches high by 32 inches long. Again, the same 1.77 square feet because we know the weight. But this particular system doesn't require the washers and the screws. In fact, you actually hide, it only takes 2 screws per panel, and you actually put those in the tongue. And on the bottom row, you've got a 3rd screw down here on the corner to lock it in. And from there on out, you're just basically stacking the interlock, got it backwards, the interlock, the bottom is locked because this is a groove, this is a tongue, no need for a screw on the bottom. Again, you're just putting 2 screws on each top. And also, where in this particular system, if you did a corner, you had to cut and turn the corner, and that wasn't an interlocking corner, it was 2 panels making a corner. Well, in the new system, I came up with 4 different sizes of inside and outside corners that allowed me to deal with corners readily. Now, another thing in fire training centers, because they're multiple, you know, 2, 3, 4 story tall, they use a lot of steel beams and posts that have to be wrapped. And the building wall is here, and there'll be a post here. So I made interlocking, what I call beam wrap posts, that allowed me to literally go inside corner, outside corner. The beam wraps would allow me to come around a beam and literally just knock it out with, I'm going backwards, knock it out with a interlocking corner system. Now, in a lot of cases, the length of this panel does not fit the length of a building. So the reason I went to tongue and groove is because I could set up a router table. Let's just say I cut this panel, boom, and now it doesn't have a tongue or a groove. So with a router table and or a handheld router, I came up with the very tongue and groove that I made this originally from, and I could put this composite is cementatious, but yet it doesn't take diamond blades. It cuts with a regular skill saw. It screws with a regular wood bit. These are just wood type of tongue and groove, and we set it up on a router table, and you can just run your cut piece and reprofile either the groove, the tongue, or the groove. This system didn't have that. The new system did. It was much more agile. It didn't require washers. It took less screws, and the screws or the fasteners were hidden. And still yet, my fire impingement and watershed was enhanced. So I had better impingement protection and better water intrusion aspects to it. So that's, and the formula, I also made the formula a slight change, a pretty massive change actually, and reinforced each panel with mesh, which gave me further strength. So as I've come around this system, I've tried to design it for many more applications, first of all and foremost, and the ease of all applications. Now keep in mind, this product, this formulation, can be inserted into a mold of all kinds of shapes and sizes, all kinds of applications. There are fireplaces that are, you know, in common thought, it is the thought that cements can take temperature, high temperature. They can't. This particular cementatious product can. Most cements will succumb to fire. Like in a fire in a home, a wood burning fire that's made, it's got fire brick that line it. And there's a reason they use fire brick clay, because it will take the heat and won't explode and crack. Cements won't. You don't just go mortar in a firebox. And there are pizza ovens, there are safe rooms, there are fireproofing in homes, in safes, refractory applications, all kinds of applications where you've got high temperature or flame that you're trying to protect against. So this doesn't have to be just a generic smooth face, a Maltese cross in the 16 by 16. This was just an image for lining a fire training center. In applications that are different, I can show you over here a SIPS panel system, which I took the same formulation okay? And I said, lining a fire training center makes no sense. We're building a building that can't take the fire. Oh, but we'll line it. Well, that doesn't make sense. Why don't we start out by building the building with material that can take the temperature without an issue? So I came up with a panel system, not a liner, but a wall, floor, and roof and ceiling panel system that interlocks, that you build the fire training center with, and it no longer needs to be lined, and it's structural. So I'm going to show you those images now of some samples that I've got over here. But keep in mind that your panel, your liner, whatever, it could look like bamboo, it could look like brick, it could look like rock, it could look like stucco, like siding, anything you want it to look like. You prototype, you make molds, and then you take the formula and cast into it. It doesn't have to be smooth and generic. That's all my point was. This is a 6-panel system that we build homes with. Now this is a quarter scale. Again, the panels are normally 12 foot by 4 foot, and this one here is only 3 by 1. So it's a quarter scale, but in this particular case, we've prototyped stack stone, which then had stucco as the upper part, and it was molded. So if you look at the panel over here, the inside panel is just smooth, like a drywall. The only thing you got to do is tape it and compound joint it and splatter it when you're done, or whatever texture you want to put with drywall. The outside has whatever the motif of the home or building that's going to be desired. Why build a building and then have to come in and drywall it? Why build a building and then have to come back and put siding or stack stone or stucco or whatever? Why not make it from the start to where it's an interlocking panel system that's got the insulation, it's fused together, and it can't burn, it doesn't warp, it doesn't rot, you don't have termite or insect issues, rodents, nothing. This system here is, again, it's molded, whatever the motif that you want to come out with. We have also made what is another version of this, which I got to get back. We made another version of this where, again, it had the stacked stone. And this can be any kind of a stone. It doesn't even have to be stone. It could be brick, whatever you want. This is a scaled down version of the James Hardie siding, which is a cement board. Again, it's molded, not put to where you have a desire to build a building that's just flat and then you come by and put the siding. This is all molded into it. The other thing that's real nice is we have manufactured into it conduit that allows for electrical or plumbing runs. At this particular panel height, you've got 45 inches and 16. The other thing is vertically, there's a conduit every 2 foot running the length of the building. So in this particular case, what I did with obviously this is a urethane. This is a EPS foam, and again, that one's a urethane. This here is what I'll call the fire training center building material, because it is designed to be the panel. It's got a different type of an interlock, which would be classified as a tongue and groove, a lot stronger. And the interior, instead of being an EPS or a urethane foam, which melt and or burn, now really urethane doesn't melt, it burns at a temperature of anywhere from 300 to 400, but it's got a 4-hour rating, for burning. This particular filler material here is sought to be lightweight. I don't want to just cast that full of cement. We've got our outside panel and our interior is made with the same formula, only a lot of lightweight aggregate has been made. Used so that it would be lighter weight and yet will not burn, because it's a fire resistant material. So again, it can take the temperature, but no liner system here. In this particular case, we've scratch coated this because they're going to stucco over it. Again, what is the exterior of your building? What do you want it to look like? Well, that's what that mold should have been. In our case, it was just a scratch coat. On the interior, we sought a smooth, kind of like the liner system, where you'd see a joint every 4 feet. These panels can be any dimension you want, but in this particular case, I think we were 12 by 4, and this is just a smooth finish on the inside. So again, this could be molded into whatever you want it to look like. In this case, it's just a generic thing. Now, I'm hearing this. This is what we put up the bottom and the top. This gets secured, a channel, stainless steel or galvanized, gets secured to the slab, and then the panels have grooves in them on the bottom where this fits inside of the panel. If you'll notice, this is just inside where the filler mix is. This is just inside of that, so that the panel fits over this, and then you screw through the bottom and you hit the steel, and that keeps it tight, or it mounts it. So again, hurricane, tornado, all these types of things, when your building is mounted to the deck and it's screwed, every vertical joint and every horizontal, it can't be taken up by the wind. And the roof the same way. All elements are all caulked and screwed together in this system. Just walk around one more time. Now this is an interior wall right here. It's just shown to be, let me raise this up. This is just an interior wall panel that I just set on the table for display purposes, but that's what that is. It's a little smaller. These panels, because of home building, is a 5.5 inch, just like a 2x6 would be. So it makes use of the door frames and windows that are now currently available. In this particular case, what you have here, unlike most panel systems, is we didn't form this corner by taking two panels and screwing them together. We've actually casted an interlocking corner, and they're outside and inside corners. So this is an outside. But the formidable strength that this adds to a building's strength is just unparalleled. It will give you a lot more strength because it's a molded, monolithic, casted piece. It does not give.